All right, physics. I had a few questions asked of me. If I could go over a few questions specifically, so far, I haven't gotten all the homework for the bank curves yet, but specifically so far 15, 16, 17, 18, and 20. Those are the ones that I have on my list. If there are other ones you want me to go over, please just let me know. But at this point, those are the ones that I'm going to go over. So 15 to 18 talked about the whole twirling the yo-yo or whatever around in a circle. So when we did the example, we talked about what is the minimum velocity that it can go and still keep the tension and still keep the circular path. And one of the things that I had said was really minimum velocity happens when the yo-yo was at the top of the circle. That's when the minimum velocity happened. But in question 15, it says a boy is twirling a 155-gram ball on a 1.65 meter string in a horizontal circle. So just spinning it. The string will break if the tension reaches 208 newtons. So what is the maximum speed that it can go? So maximum speed based on the tension is actually going to happen when the yo-yo is at the side, because when it's at the side, right, force of gravity is going this way. Force of tension is the only thing center seeking. It is the only thing going into the circle, and this is working completely perpendicular to it, and we never look like X and Y are separate. So my max velocity is actually going to happen when my centripetal force is equal to just my force of tension. So centripetal force is mass times velocity squared over r. Force of tension, well, they told me that the max that the string can handle is 208 newtons. So the mass is 155 grams, so that's 0.155. I'm looking for V. The R is 1.65 because they said the string was 1.65 meters, and that's equal to 208. So 208 times 1.65 divided by 0.155, then take the square root. I got 47.0 meters per second. Someone said that they thought, not for this one, but I think 16, they thought the answer at the back of the book was wrong. So be checking your answers. I know these answers are right because I've done them for many years now. All right. 16. 16 says an electron, oh yeah, because we're dealing with small stuff. An electron has a mass of 9.11 times 10 to the negative 31st kilograms. That is a horrible number. So if you don't know how to really efficiently put stuff in scientific notation in your calculator, that can be an issue. Now it orbits a hydrogen nucleus at a radius of 5.3 times 10 to the negative 11th meters. So this is my radius, this is my mass. Whew. It says find the centripetal force acting on the electron and what type of force supplies that centripetal force. So centripetal force is mv squared over r. trying to see what I did. How did I get that? Oh, that's because I missed something. The speed is 2.2 times 10 to the 6 meters per second. It helps if I read the whole question, huh? I was looking at my work going, where did I get that number? Well, that's because it's there. 2.2 times 10 to the 6 meters per second. So this really should be just a matter of putting the numbers in. 9.11 times 10 to the negative 31st times 2.2 times 10 to the 6th, but that is squared, over r, which is 5.3 times 10 to the negative 11th. So that can be tricky to get into your calculator correctly, so just be careful with that. I would actually do this first, then multiply by this, then divide by this. I got 8.3 times 10 to the negative 8 newtons when I did that. It is a centripetal force. Someone said the units at the back weren't right, like they weren't finding force, they were finding something else. But that is really the force. The question is, what type of force supplies the centripetal force? Electromagnetic? No, maybe. Gravity, maybe. It's a chemistry question. I don't know. So, yeah, I think it would be an electric field. Yeah, I think it would be magnetic. It would be magnetism, I think. Number 17, there was an A, a B, and a C. All right. That did not look like fun. I have a lot of work. Okay. So, it says you have a stone that has a mass of 284 grams. So 0.284 kilograms. And it's twirled at a constant speed of 12.4 meters per second. In a vertical circle with a radius of 0.850 meters. Alrighty. So they want to know, what is the tension in the string at the top, at the bottom, and what is the maximum speed the stone can have if the string will break when the tension reaches 33.7 newtons. All right, so here's what I did. I'd love to tell you why I did this. I don't think I can. So at the top, we have force of tension and force of gravity both working in that direction. So I said for the top, I said that centripetal force is equal to force of tension plus force of gravity. So I did mass times velocity squared over r is equal to force of tension plus my mass times my gravity. So then I just filled everything in. 0.284 times 12.4 squared over 0.850 is equal to force of tension plus mass, which is 0.284 times 9.81. So I figured out what this was, and I moved this over here and subtracted it, and I got that the force of tension was 48.6 newtons. So at the top, that's what I got. Then they wanted to know at the bottom. At the bottom, right? Yep. At the bottom, force of tension is going towards the center of the circle. Force of gravity, though, is going opposite to it. It's pulling down. So, centripetal force then is equal to my force of tension minus my force of gravity in this case. So, again, I would do exactly the same numbers, but this time when I move this over here, I would end up adding it. And so I got that my force of tension was 54.2 newtons, okay? Now, it says, what is the maximum speed that a stone can have if the string will break when the tension reaches 33.7? Now, can I tell you I did two separate things for part C? I did, at first, I did what I did in the last question, and I made centripetal force equal force of tension, and I got 10 meters per second. However, I crossed that out. So I'm gonna have to do some looking into this. So I will get back to you. I'm doing that thing again. Because what I ended up doing was force of tension minus my force of gravity. So doing this scenario again at the bottom is equal to my centripetal force. And when I did that, my force of tension was 33.7 because they said the string will break under 33.7 newtons of tension. And so then I ended up doing minus 0.284 times 9.81 for force of gravity, and then I did mass 0.284 times velocity squared over r squared, and my r is 0.850. And so I ended up doing that and solving for v, and I got 9.62 meters per second. Now you're asking the same question I am, and that is why in the other one did we figure out max when it was at its side and this one down at the bottom? My answer, I honestly don't know. So I'm going to do some research on that, and I'm going to answer that question hopefully by tomorrow, if not the day after. But I will let you know, okay? 18, because when I don't understand something, it bugs me. Number 18 says you are driving a 1,654 kilogram car on a level road surface. So my mass, 1,654, I think it said. And you start to go around a curve, and you are going at 77 kilometers per hour. It says the radius of the curve is 129 meters. The question is, if that is the radius, what has to be the frictional force between the tires and the road so that you can safely make the turn? So the only thing holding you to the road, because it's not a banked curve, the only thing holding you to the road is force of friction. So that means my centripetal force would have to equal my force of friction. So centripetal force is mass, which is 1,654, times velocity. Now here's the problem. Velocity is in kilometers per hour, so you need to change that. So if you have 77 kilometers per hour, and I know there are 1,000 meters in 1 kilometer. Again, I put the kilometers on the bottom and the meters on the top so that my kilometer units would cancel. And I know that in 1 hour, there are 3,600 seconds. So this way my hours cancel and the units I have left are meters per second. So 77 times 1,000 divided by 3,600 turns out to be 21.4 meters per second. So my velocity is 21.4 squared over r, which is 129. So when I worked that out, it turned out to be, I can only have two significant figures because it was 77. So I got 5,900 newtons of frictional force is what I would need. Okay. And finally, we have 20. 20 was asked of me. So I gotta flip over, hold on. So we have the formula for banked curves. Tan theta is equal to v squared over r times g. That's the formula that we have. And number 20 says an engineer designed a turn on a road so that a 1,225 kilogram car would need 4,825 newtons of centripetal force. When traveling around the curve at 72.5 kilometers per hour. Question is, what is the radius of the road? What is the radius of the road? This is a trick question. Does it say anything about that he banked the curve? Nope. Doesn't say anything. It doesn't give an angle that he banked the curve. He didn't bank the curve. So since it doesn't say anything, I'm not actually going to use that formula because there is no angle in it. He didn't bank the curve. He didn't make the curve. So centripetal force is equal to mass times velocity squared over r. They said the centripetal force is 4,825. My mass is 1,225. V squared. Now they have it in kilometers per hour. You need to change that into meters per second. Turns out it's 20.14. Do it just how I explained the last one. Over r. R is what we're looking for. And so I would solve for that. I would do this times this and divide by this, right? And that's just a matter of rearranging the formula. My r worked out to be 84 meters. So even though it's in this section on banked curves, this one didn't actually have anything to do with banked curves. It's a trick. All right. So I'm going to figure that difference between 15 and 17 out. Why did they do it differently? I'm going to figure that out. Beyond that, though, to review, we're going to have a test, remember, on Friday, right? I have it all. Yeah. We're going to have a test on Friday. So there's no work to do per se today, and tomorrow will be a study day. I'm going to start into chapter 12 on Thursday. Just barely start into it. And then your test, we will do it via Zoom at 11 o'clock on Friday. So chapter 11, just to really quickly go over it. I posted both of the PowerPoints. They should be in the first day we did 11.1 and the first day we did 11.2. It should be in the title. Shouldn't be too hard to find. You do need to know terms like trajectory, projectile, range, things like that. You need to know, it talked about points, things that will help you analyze projectile motion. The fact that no forces affect horizontal motion, so the equation of uniform motion applies. Gravity only affects the vertical motion. Time is the thing that connects them. We talked about that. We did some questions where the initial there is an initial horizontal velocity, but no vertical velocity. No initial vertical velocity. So some questions like that. Then we started doing projectiles launched at an angle, which ends up giving a parabola. So in that case, your initial velocity is at an angle, so we had to break that apart into components, into an initial y velocity and an initial x velocity. And then we did the symmetrical trajectories. If it takes off from the same height that it lands at, it makes symmetrical. And there were 3 formulas, one for figuring out the time of the flight, one for figuring out the max height of the parabola, and one for figuring out the horizontal distance or the range that it goes. Section 11.2 talked about centripetal force, centripetal acceleration. Again, those are some terms that you will need to know. We did some questions regarding that. We talked about what's the difference between centripetal force and centrifugal force. Remember, centripetal force is an actual force, center-seeking force, whereas centrifugal force is a fictitious force that you feel when you're in a non-inertial frame of reference, I think, and when you're in a moving frame of reference or an accelerating frame of reference. Then we did banked curves, and honestly, that's pretty much it. Chapter 11 is not super long. It's just not. And that's it. So I will figure out those answers. If you have any questions you want me to go over, please let me know. So we talked about, when we talked about bank curves, we talked about why do they bank curves, and they bank the curves so that gravity so that you don't need as much friction to keep you on the road. Some of that normal force can go towards centrifugal force, and it doesn't, the centrifugal force doesn't all have to come from the force of friction. Remember that centripetal force is a force that is supplied by another force. That centripetal force comes from somewhere. So if you've got the sun and planets going around it, and we're going to talk about that in the next chapter, but what keeps the planets going in orbit is centripetal force, but what is supplying that centripetal force would be gravity. When you're spinning a yo-yo around, tension, and at some points, gravity. Friction can supply it. Even magnetic, when we talked about the electron going around, that's electromagnetic force that's keeping that in place. There's lots of different forces that can supply it. Like I said, know your terms. We're going to do it via Zoom because the first part of the test is theory, and then the next part of the test is the math. So if you have any questions, please just let me know. And yeah, we'll see how all that goes. All right, talk to you again soon.